Sometimes the most common everyday materials hold the deepest secrets. We think we know something like steel, right? We've been using it forever. But it turns out if you push it to the absolute limit, it starts to break all the rules we thought we knew. Okay, let's get into this.
So what you're looking at here is a tiny cross-section of a steel weld. Seems simple enough, but locked inside that little fusion of metal is a phenomenon that just completely defied decades of scientific predictions. It's this wild mystery that only happens in a few milliseconds, and to solve it, researchers literally had to build a camera fast enough to watch atoms in motion.
All right, so before we get to the cool rule-breaking part, we gotta understand what the rules are in the first place. See, under normal conditions, welding this type of steel is actually a very predictable, well-understood process.
When this particular steel alloy cools down at a normal pace, its atoms lock into this very distinct kind of branch-like pattern you see here. This is the visual signature of a crystal structure called delta ferrite, or delta ferrite for short.
Think of it like this. When the molten steel needs to turn solid, delta ferrite is the most stable, most comfortable shape for the atoms to snap into. It's the thermodynamic favorite, it's the path of least resistance. All of our models, all of our predictions say this is the structure that should form first. It's the expected winner every single time.
And our predictions get even more specific. Depending on the exact chemical recipe of the weld, like say how much aluminum you've got in the mix, we have these incredibly powerful models that can tell us exactly which microscopic impurities, which are called inclusions, will pop up. Got a lot of aluminum, you're going to get aluminum nitride. Less aluminum, you get aluminum oxide. It's just incredibly precise.
So, the main takeaway here is that, under normal circumstances, the science is totally settled. We know what to expect, from the big crystal structures all the way down to the tiniest little impurities. Our models, they nail it perfectly. But what happens when the circumstances are anything but normal?
And this is where our story really gets interesting. Researchers decided to ask, hey, what happens if you take this normal, predictable process and just crank the speed dial all the way to 11?
And we are not talking about a small change here. The cooling rates they used were over 1,000 Kelvin per second. To put that in perspective, that's anywhere from 10 to 50 times faster than a normal weld. It's like the difference between a pot of water cooling on your stove and flash freezing it with liquid nitrogen. It's that extreme.
So this is the big question, the one that drives this entire investigation. When you force steel to solidify in literally the blink of an eye, does that stable, predictable delta ferrite still have time to form? Or does something else entirely take over?
Now, answering a question like that is a huge challenge. I mean, you can't just point your phone camera at it and call it a day. You need to see the unseeable, and to do that, you need a very, very special kind of tool.
The entire event, the whole mystery we're trying to solve, is over and done with in less time than it takes you to blink. We need to somehow capture that exact moment when the very first solid crystals start to form out of that liquid metal.
So meet the hero of our story, the synchrotron. Now this isn't your regular X-ray machine. This is a massive particle accelerator, like the size of a stadium, that generates X-ray beams billions of times brighter than the ones at a hospital. It basically lets scientists make a super slow-motion movie of atoms as they move around, taking snapshots every 50 milliseconds. It's the perfect tool for this job.
So here's the setup. The researchers create this tiny little weld pool, and they hold it perfectly still right in the path of that powerful synchrotron beam. And they take readings at two critical spots. Location B, which is the solid steel right at the edge of the melted part, that's called the heat-affected zone, and location A, right in the molten center, the fusion zone, as it cools and solidifies.
And what that super-powered camera saw, well, it completely upended everything we thought we knew. The results were not what anyone was expecting. Okay, so first, let's look at the edge of the weld, that heat-affected zone. The data from this spot is really fascinating. As the metal gets super hot but doesn't quite melt, we see signals for both delta ferrite, our predicted winner, and another crystal structure called austenite. Now, austenite is usually less stable at these temperatures, so it's like they're both there, side by side on the solid shore of this liquid pool, just waiting for their chance to grow.
And now, the moment of truth. The molten fusion zone. As it flash cools, the X-ray data tells the whole story, and it is a shocker. There is zero signal for delta ferrite, none. It never even forms. Instead, the signals for austenite just appear out of nowhere, straight from the liquid, and get stronger. The predicted winner didn't even show up to the race. Austenite won instead.
I mean, the contrast here just couldn't be more stark. All the equilibrium predictions, the ones based on slow cooling, said the liquid steel should solidify into delta ferrite. But the reality, captured in real time by the synchrotron during that rapid cooling, shows it solidifies directly into austenite. The rulebook was just completely thrown out the window.
And if you need to see it to believe it, here's the visual proof. On the left, you see that skeletal delta ferrite that forms in a normal, slow weld. And on the right, that's the microstructure from the rapid weld. It's a totally different material. None of that skeletal structure is there. It's night and day. This is the microscopic evidence that confirms what the synchrotron saw happen in real time.
So this brings us to the really big question, right? Why? Why did the underdog, austenite, suddenly win the race when things got so extreme? The answer, it turns out, has huge implications for how we design and build things.
You know, the best way to think about this is like a race. Delta ferrite, our predicted winner, is like a marathon runner. It's more stable, more energy efficient, and over a long race, it will always win. Austenite, on the other hand, is a sprinter. It's less stable, but man, it can form much, much faster. In a normal, slow-cooling marathon, the steady runner always wins. But in the lightning-fast sprint of this experiment, the quicker sprinter, austenite, gets such a massive head start that it finishes the entire race before the marathon runner even gets going. It's a classic case of what scientists call non-equilibrium physics, where pure speed literally changes the outcome.
And believe me, this isn't just some academic curiosity. That first crystal structure that forms, it's like the foundation of a house. It dictates everything that comes after it. It sets the whole pattern for the final microstructure, which in turn determines the most important things about the material, like its strength and how resistant it is to cracking. So understanding that we can actually switch between these two outcomes gives engineers a powerful new tool to create stronger, tougher, and more reliable materials for everything from bridges to spacecraft.
And you don't have to take my word for it. As the researchers themselves put it, this discovery isn't just about explaining some weird result. It's about creating a science-based roadmap for designing the next generation of materials and welding processes. By controlling the speed, we can control the final structure, and we can build things better, stronger, and safer.
It just leaves you with this one last thought. We have been working with steel for centuries, literally centuries, and it still had this incredible secret hidden away at a timescale we could barely even measure until now. It really makes you wonder, right? What other fundamental rules of the materials all around us are just waiting to be broken if only we can figure out how to look fast enough to see them?